Okay, so now we can move on to proving that closed sets are also relatively additive. Now, it should come as no surprise that we can give a slightly more direct proof for this case, since we've already done work to establish the case for open sets. Yeah, let's take any closed set, right? F is going to be a closed set of real numbers. A is going to be any set that is disjoint from F, but could be any set of real numbers so long as it is disjoint. And just like last time, we are going to prove that the sum over the lengths is greater than or equal to this thing. So if you go back and compare what we did, what our broad strategy was for open sets, it is the same broad strategy that we're going to use here. So I won't explain it too much. But we can do a little bit of shortcuts because of what we already have for open sets. In particular, what you can kind of realize is that because A and F are disjoint, then A being covered by this union of open interval, right? This is an open interval cover of the union, so it also must cover A. And if you delete out from it F, well, F and A are disjoint, so you're not losing any of the elements that are in A. So A is contained in this. And that's kind of nice because this is transparently an open set, because effectively, right, if you translate this set minus into the intersection of the complement, then F complement is open, and intersecting an open set with an open set is open. So this is an open set. And therefore, because it's open, we can leverage what we've already done, which is to take this, decompose it into its parts, use the fact that this part is, decompose it according to F, so to speak. This part is open, apply relative additivity. So you get this. And so now let's start kind of, right, like in particular, we're interested in this part because we're going to relate it back up to here, right? So if we apply monotonicity, then we get that m star of A is less than or equal to m star of this thing. So if you took, right, and that's the same thing as this. So if you solve this, right, take this and move it to the other side, especially, right, you move it, right, subtract it off of here. And I guess I'm now realizing that this argument works only if you know that m star of F is finite, but the proof for the case where m star of F is infinite will be just as easy as it was for the open set case. So, you know, I'm going to leave that, right? Basically, I already proved it. Nothing about that earlier proof depended on the set being open or not. So we can take this to be finite because the proof for infinite is just like the last one. So we subtract this over to here, and so we say that we can replace this thing with this minus m star F, right? So you get this, basically, right? That's the upshot. So m star A less than or equal to this thing. Now, we've already seen before how m star of a union of these intervals is less than or equal to the sum over the lengths. Now, okay, that's actually really simple because that's subadditivity. And then you're pretty much done, because all you have to do is take this, add it over to here. You have this part. Just like last time, the reverse is done by subadditivity, and the proof is complete.